Example 11.1 Stress and strain. When a load of 16 kg, this M, is hung vertically at the end of a 5 meter long. This is our original length. The extension produced in the wire is this. What is this? Is delta L, or the symbol is E, elongation. If the cross-sectional area is this, what is this? This is cross-sectional area. So calculate the strain. And the symbol is here, strain. Okay, we draw the picture of the situation. When a load of 16 kg is hung vertically, so we have a long wire here. It hung vertically like this. So which force that acted to the load? Now we have weight. What else? There's a string, a wire, right? So there is a tension in the wire. So here is the direction of tension, and we get the force there now is tension. Okay. So weight is equal to mass times gravitational acceleration, and it's given 16 gravitational acceleration and 9.81, and I get here 156.6 Newton there. So the strain here is equal to the elongation delta L divided by the original length. All the values are given, right? So delta L is, we just substitute, divided by original length 5 meter, and I get the answer 7.6 times 10 to the power of -4. So there's no unit there because here is the unit is meter, right? And here also the unit is meter, and they cancel each other. And B, stress. What is the formula of stress? Stress is equal to force divided by cross-sectional area. And for this case, the force that acted to the long wire is weight. And what is weight? Weight is equal to mg, and we get there the value is 156.96 divided, and the cross-sectional area also given, so 1 times 10 to the power of -3, and I get the answer 1.57 times 10 to the power of 5, and the unit is Newton per square meter. Example 11.2 Young modulus. Refer to the example 11.1. Calculate the Young modulus of the wire. Okay, what is the formula for Young modulus? Yang modulus, the symbol is capital Y equal to stress divided by strain. And from the previous example, we get the value of stress is this, and the value of strain is this. And we calculated it and we get 2.07 times 10 to the power of 8, and the unit is Newton per square meter. Example 11.3, strain energy. A thin steel wire, initially 1.5 meter. What is this? This is original length, long and a diameter of 5 times 10 to the power of negative 3 meter. So this diameter then is suspended from a rigid support when a mass of 3 kilograms. So what is this? This M is attached to the lower end of the wire. It elongates this. What is this? This elongation of the symbol of delta L. Calculate the strain energy. Strain energy U is stored in the wire. Okay, so strain energy U is equal to half force times elongation. Okay, so now what is the force acted to the steel, the thin steel wire? So we draw it here, and what is the force that acted? So the answer is weight. Weight equal to mass times gravitational acceleration, and we get the mass here is 3 times 9.81, and I get the answer 29.43 Newton. Okay, so do we have the value of, yes, this is the value of elongation. So we just substitute the values. Now the force here is the weight there, and the elongation, just put it, and then we calculate it carefully, and I get the answer 1.66 times 10 to the power of negative 2 is energy, so the unit is joule. Example 11.4, strain energy per volume. Refer to example 11.3, the previous example. Calculate the strain energy per volume. So strain energy per volume of the wire. So strain energy per volume. So that means we have to find the volume of the wire. So we draw the wire. This is the cross-sectional area A, and this is the length of the wire. So this is the original length, and this is the L0. So how do we gonna find the volume here? So the volume is equal to cross-sectional area times the original length. Do we have the value of do we are given the cross-sectional area? No, but we have the diameter here. It's given the diameter, so that means we have to find the area first using the diameter, and we will use this formula divided by 4, and we substitute it very carefully, and the diameter is what? 5 times 10 to the power of -3. Don't forget to square them. Whatever 4, I get the answer is 1.96 times 10 to the power of -5. And the unit is this area, right? So, square meter. So, now we can calculate the volume of the thin wire. Okay, we substitute it very carefully. And the original length is given in the equation initially 1.5. Okay, and I get the answer is 2.94 times 10 to the power of -5. So this is now volume, so the unit is cubic meter. So now we get the value of volume. We can just substitute the value of strain energy that we calculate here in the previous example. And strain energy 1.66 times 10 to the power of -2, and we divided by volume 2.94 times 10 to the power of -5. And I get the answer is 564.63. So upper joule, lower is a cube per cubic meter.
Question number 1. Two metallic rods X and Y with similar length and cross-sectional area are joined together and insulated. At a steady state, the temperatures of rod X and rod Y are 100 degrees Celsius and 40 degrees Celsius, respectively at each end as shown in figure 13.1. The thermal conductivity of X is twice the value of Y. Calculate the temperature at the junction between X and Y. From the question itself, we know that both metallic rods have the same length and cross-sectional area, while the word insulated itself means that there will be no energy loss towards the surrounding, thus rate of heat transfer should be constant. Aside from that, it is clearly stated that the value of Kx is twice of Ky in this situation. Bear in mind that whenever two metals or any conducting materials that are different in temperatures come in contact, the heat will flow from the hotter metal to colder metal. As for our reference, we will put a note that T1 is at 100 degrees Celsius, T2 is the temperature at the junction, and T3 is at the 40 degrees Celsius end. I put it this way since heat conduct from hotter to colder area. Well, it helps a lot actually, so that you won't get it mixed up when you are going to substitute these values in the equation later on. So in order to find the temperature at the junction of these two metals, rod X and rod Y, we can use the rate of heat transfer from the equation for both of them. Substitute the equation with the known data that we gathered earlier. So dq over dt for X and dq over dt for Y. So we get all the data that we have and substitute into these equations. And later on, you will get the value of the temperature at the junction between X and Y is 80 degrees Celsius. Let's move on to question number 2. An aluminum rod has a diameter of 3 cm and a thickness of 0.6 meter. One end of the rod is placed in boiling water and the other end is in ice. Calculate the quantity of heat transferred through the rod within 1 minute. Given that the thermal conductivity of the aluminum rod is 205 watt per meter per Kelvin. So now we have a metal with one end in the boiling water that is at 100 degrees Celsius and the other end is in ice at 0 degrees Celsius. It's okay for us to change the unit of degrees Celsius into Kelvin since delta T or dt here is just the temperature difference. But for unit of time, the unit must be in seconds. Applying the rate of heat transfer equation, where the cross-sectional area of a cylinder is a circle, which is pi r square. Substitute the other values, and therefore, the quantity of heat transfer through the rod is 1449.06 joule. Question number 3. Two insulated metals, plumbum and copper, with a thickness of 40 mm and 60 mm respectively, are joining together. The temperature of plumbum is fixed at 70 degrees Celsius and copper is at 30 degrees Celsius. If the thermal conductivity of the copper is 4 times of the thermal conductivity of plumbum, calculate the temperature at the junction in steady state. Assume that the cross-sectional area are the same. So we extract that data. We know that the thermal conductivity of the copper is 4 times of the thermal conductivity of plumbum, and the area for both metals are the same, which will give us the value of A. So, by using the same equation as previous question, so we substitute the value into this equation, and then finally we will get the answer. The temperature at the junction is found to be 40.91 degrees Celsius. Move on to the next question, question number 4. Two metal bars X and Y have the lengths of 70 cm and 30 cm as shown in figure 13.2. Both have the same cross-sectional area. At one end of the metal X, heat supplied from boiling water at 100 degrees Celsius, and one end of the metal Y is placed in melting ice at 0 degrees Celsius. Both metals are well insulated. The temperature at the junction is 15 degrees Celsius. Calculate the ratio of thermal conductivity between metal X and Y. Assume that the heat flow is steady and no energy is lost due to the surroundings. So we have two metals, X and Y, and they are both in contact. What we know that both of them have the same cross-sectional area, which gives the value of A. And the temperature at the end of X rod is 100 degrees Celsius, and at the other end is at 0 degrees Celsius. And given to us for this question is the temperature at the junction, which is found to be 15 degrees Celsius. Again, the case that we have right now is insulated, where we take note that there no energy loss and rate of heat transfer should be constant. So by applying the rate of heat transfer equation, thus we'll get the ratio of thermal conductivity between metal X and Y is 0.412. There's no need to write the unit in this case because they ask for the ratio. Question number 5. The rate of heat conduction is 80 kJ per hour at a thin wall with an area of 14 cm square. If the temperature gradient across the wall is 15 degrees Celsius per meter, calculate the thermal conductivity of the wall. So we extract the data. Right now, they give us the value of the rate of heat conduction, the area, and also the temperature gradient, which refers to the value of dT over X. That is your temperature gradient, which is found to be 15 degrees Celsius per meter. So we have our rate of heat transfer equation and rearrange it, and we can find the value of the thermal conductivity of the wall is 105.07 watt per meter per Kelvin. Question number 6. A 100 cm rod A expands by 8 mm when heated from 0 degrees Celsius to 100 degrees Celsius. Calculate the coefficient of linear expansion for rod A. So for this question, this is what we have been discussed in the second subtopic of the chapter, which is thermal expansion. Given to us, length of the rod is 1 meter and it expands on its length, which is 8 millimeters. So it expands linearly. Using the linear expansion equation, which is delta L equals to alpha L naught delta T, we rearrange the value and substitute all the data that we have extracted from the question. And finally, the coefficient of linear expansion is 8 times 10 power of negative 5 per Celsius. We are now at question 7. A technician cuts a hole of area 2.0 centimeter square through a copper sheet. The temperature of the sheet rises to 150 degrees Celsius. Find the area of the hole in centimeter square when the sheet is cooled down to room temperature, 30 degrees Celsius. Given that the coefficient of linear expansion of copper is 1.7 times 10 power of negative 5 per Kelvin. So for question number 7, like usual, we extract the data from the question. In this case, the area of the hole will shrink since the temperature is cooled down to 30 degrees Celsius. By using the area expansion formula, delta A equals to beta A naught delta T, then we expand the formula. Take note that in the question, they gave us the value of for coefficient of linear expansion, also known as alpha. You should know by now that for the same material, the coefficient of expansion beta is twice the value of alpha. So substitute that into our equation. And finally, we get the area of the hole will become 1.99 cm square after the sheet is cooled down. Question 8. A 60-liter steel tank is full of petrol at a temperature of 30 degrees Celsius. If the lid of the tank is not tight, how much petrol will spill out at 40 degrees Celsius? Given to us, coefficient of linear expansion of steel is 1.2 times 10 power of negative 5 per Kelvin, and coefficient of volume expansion of petrol is 9.5 times 10 power of negative 4 per Kelvin. So, 60 liters is equivalent to 60 times 10 power of 3 centimeter cube. The initial temperature is at 30 degrees Celsius and the final temperature is at 40 degrees Celsius. So the value of alpha for steel and gamma for petrol is given. The 60-liter petrol is filled inside a steel tank with maximum capacity of 60 liters. Since the temperature is risen, both liquid petrol and the steel tank are expanding. We expect that there will be petrol spill out if the steel tank expands less than the liquid. So for now, we should find the value of volume of petrol at 40 degrees Celsius by using the equation for volume expansion, which is V equals to V naught plus gamma V naught delta T. We expand the equation, substitute the equation with the data that we have extracted earlier, and we get the value of volume. Petrol volume is at 60,570 centimeter cube. Next, you should know that the value of coefficient of volume expansion is 3 times of the value of linear expansion of the same material, which means it is gamma is equals to 3 alpha. So volume of steel at 40 degrees Celsius, we can get it as 60,021.6 centimeter cube. And finally, we can calculate the volume spill out by using this formula. Delta V equals to V petrol minus V steel. And finally, we get the answer, which is 548.4 centimeter cube. Question number 10. A glass window of cross-sectional area 1.5 meter square and thickness 0.2 cm is closed in winter. The temperatures of the inner and outer surfaces of the window are 15 degrees Celsius and 0 degrees Celsius. Question A. Calculate the rate of heat flow through the window. And B. Suggest how you would reduce the amount of heat loss to the surroundings through this window. Given to us, thermal conductivity of glass is 0.84 watt per meter per Kelvin. So to tackle this question, first you should have a sketch of what were given in the question. So what we have here is a window and T outside and T inside, which refer to the same thing that they give in the question. So T outside, which is the T outer from the question, is about 0 degrees Celsius. And T inside, which is the T inner, is at 15 degrees Celsius. So what should we do next is, we just use the rate of heat flow equation, and then we just substitute the value that we already extracted from the question, and we get the value of dq over dt, which is 9,450 watt. Question number 11. A copper plate of thickness 1.0 cm is sealed to a steel plate of thickness 10 cm as shown in figure 13.3. The temperatures of the exposed surfaces of the copper and steel plates are 30 degrees Celsius and 15 degrees Celsius respectively, obviously which is at both ends. When both rods are in the steady condition, the temperature is 29.8 degrees Celsius. Determine the thermal conductivity of copper if the rate of heat flowing through the plate is 2,310 joules per minute. Assume that the cross-sectional area A are the same, given A is 50 cm square. So first, let us extract the data. The thickness of the copper is about 0.01 meter. Temperature of the copper 30 degrees Celsius, and the temperature of the steel is 15 degrees Celsius at both ends. Okay. And the temperature in between them is about 29.8 degrees Celsius. Take note that the rate of heat flowing given in this question is in unit joule per minute. So we need to change it to joule per second. So from the rate of heat flow equation, okay, so we just substitute all the value that been given, and then we can get the value for the thermal conductivity of copper is 385 watt per meter per Kelvin. Okay, we are now at the last question for this tutorial. So question number 13, a material X of length 1.0 cm is in thermal contact with another material Y of length 10 cm as shown in figure 13.4. The temperature of the exposed surface of X and Y are 30 degrees Celsius and 15 degrees Celsius respectively. Determine the temperature of the interface between the two materials, the amount of heat flowing through unit area of X and Y per second. Given to us, the thermal conductivity of X and Y are 0.13 watt per meter per Kelvin and 0.29 watt per meter per Kelvin. So, what we have to do now is we extract all the data that have been given in the question. And then, for question number A, what we need to do is, we could use the formula for rate of heat transfer for both material X and Y. And then we substitute the value into these equations. And then we finally find the value of the temperature of the interface between these two materials, which is 27.26 degrees Celsius. And next, for the same equation, we could also find the rate of heat flowing through unit area of X and Y per second. It's just simply we substitute the value that we get, and then finally the answer is 35.62 joule. So that's it for this chapter. I hope this lecture has cleared things up for you. Thank you for listening and good luck in your study. If you are pleased with this video, like and share it with your friends. And finally, don't forget to subscribe to our YouTube channel, DC Physics KMPk. Assalamualaikum and bye.